Hello everyone and welcome back to EECS 2200. So in this video we're going to start talking about the material in chapter 8, which is about natural and step responses of RLC circuits. So this is really continuing our discussions from 2 chapters ago. So in chapter 6 we started talking about capacitors and inductors, introduced them, talked about their voltage and current relationship, talked about the fact that they're storing and releasing energy kind of in electric and magnetic fields. And we learned how to combine them in series and parallel. We learned about mutual inductance. In chapter 7, we connected these elements, either a capacitor or an inductor, to a circuit that has other elements as well, such as voltage sources, current sources, or resistors. And we learned how to analyze these kind of circuits when we have one energy storing element, such as a capacitor or inductor, and the rest of the circuit is just basically sources, bunch of sources and resistors, right? We learned that how these circuits are analyzed when we basically disconnect the source from them, which we called it natural response, or we connect a new source to them, which we called it a step response. So in this chapter, we're going to talk about RLC circuits, which means we're going to have both inductors and capacitors in the circuit, and we're going to have, of course, resistors and voltage sources and whatnot as well, right? So we're going to talk again about their natural response and their step response, and basically analyze these, learn how to analyze these kind of circuits. The process is more or less the same, but it is, as you can imagine, because we have two energy storing elements, the math is going to be a little bit more complicated, but we are going to try, similar to chapter 7, that in the end we had a general solution. We're going to try to formulate the behavior of these circuits in different conditions. We're not going to have one equation, one general solution. We're going to have many of them, several of them, but then the good news is that we can formulate everything and they're very similar to each other. So, well, let's continue this discussion in the future slides, and then you will see it yourself. So if you want to connect an R and an L and a C with each other together, you can actually connect them in parallel, so something like this, or in series. So you can imagine that we're going to have series RLC and parallel RLC circuits. So we're going to actually discuss them separately. We're going to start with parallel RLCs, these kind of circuits, discuss their natural and step response, and then we're going to discuss series RLCs, natural and step response, right? The definition of natural and step response is pretty much the same. So whenever you're removing, basically the source is removed, there is no independent source in the circuit, we call it a natural response. So this is basically natural response. And so both this one and that one. And the step response would be these two. So the one on the right is actually much more clear. Why is it the step response? Because you just have a switch turning on. The one on the left is a little bit more tricky. You've seen more of these examples in the previous videos, but when the switch is closed, all of this current source's current is going to go through this short circuit. None of it is going to come here, so it's going to be zero. So it is not connected to the circuit. So the R, L, and C are not going to see any of the current source. But the moment I open the switch, this branch is actually out of the picture. So I have a current source connected to the rest of my circuit. That's why it is a step response. So after switching, after the switch is actually opened, or after t equal to 0, I have a current source connected to the rest of my circuit. Therefore, it is a step response. One thing that I wanted to mention before going to the next slide is that similar to RL and RC circuits, whenever I have an R here, it doesn't necessarily mean that I have a single resistance there, like here, for all these circuits, right? It really means the Thevenin equivalent resistance of the rest of the circuit. So we're assuming that we're going to have only one capacitor and one inductor, but there's no limit on the number of resistors that we might have in the circuit. And you're going to see many examples, and you've seen examples of this in the RL in chapter 7 when we were discussing RL and RC circuits. So back then we might have had many other resistors and voltage sources and current sources and dependent sources and independent sources. First, if we had more than one resistor, we always had to actually find the R Thevenin of that, and then basically replace the entire circuit with just one R. Now, if that circuit is in parallel with the inductor and capacitor that they have, that would be a parallel RLC. If it's in series, it would be a series RLC. That is also valid about the voltage source here, right? So like, for example, if you have a voltage source and a resistor, or in this case, you have a current source and a resistor in parallel, that's really the Thevenin or Norton equivalent of the rest of the circuit, right? So you might actually have more than one sources, but well, we need to simplify the rest of the circuit with just one source and one resistor if it's not just one source and one resistor. So I have one inductor, one capacitor, and then this side of the circuit, this could be the Thevenin equivalent of a huge circuit, a very complicated circuit that they just simplified to this form, right? So that's one point that I wanted to mention. Most of the examples that we solve, it's not going to be very complicated in terms of the number of sources and the number of resistors, but it's always important to remember that basically if you have more than one resistor, you have to replace the entire circuit with one equivalent resistance, okay?